basically about magnetic phase transitions and how this happens. So we are going to be dealing with magnetic materials, so with the materials that basically possess the magnetic properties. So there are different types of magnetic materials, ferromagnetic materials, and diamagnetic materials. But right now here we are just dealing with ferromagnetic materials for you. So in the case of a ferromagnetic material, as you can see in this diagram, they have different domains that are represented by these small blocks, and they all of these domains have different magnetic field. Their dipoles, magnetic dipoles, are aligned differently in such a way that their magnetic field intensity, the net magnetic field intensity of the material is 0. But if you start putting this material inside a magnetic field, the domains, the magnetic dipoles in a domain will align themselves such that to follow the direction of the magnetic field. But at a certain temperature, it so happens that even inside a magnetic field, the magnetic dipoles realign themselves and they don't follow the direction of magnetic field anymore. And we call such temperatures as Curie temperature.
Here we have our ferromagnetic material. This ferromagnetic material is in the presence of this magnetic field. So right now all of its domains are aligned with this magnetic field and it's attracting this magnet. Right now it's magnetized. It's connected to this magnet. Once we apply some voltage across it, with essentially giving it energy. So once its energy increases, its temperature increases. So as its temperature increases, at a certain temperature called the Curie temperature, this wire will demagnetize and it will detach from this magnet. So, and we know that the total energy supplied to this wire is equal to the energy absorbed by the wire plus the energy radiated by the wire. So the total energy supplied to the wire is the amount of voltage times the current supplied times the time it took for it to detach. So this is the time when Curie temperature was reached. This is equal to the energy absorbed. Energy absorbed is the mass of the wire times the specific heat capacity of the wire times the change in temperature. That is, this is our starting temperature and this is our Curie temperature. At this temperature, time will be 0 and we will stop the experiment. The energy radiated is the emissivity times the Boltzmann constant times the surface area times the change in temperature power of 4. So in fact this is Curie temperature times the power of 4 minus the initial temperature times the power of 4. Mental setup. This is our wire. So this wire right now, as you can see, it's attaching to the permanent magnet right here. See? So these are our wires which will supply us our electricity. It goes on till the mains. This is our safety box. So if the voltage increases more than a certain value, these breakers will trip and no more voltage. So this is just our safety precaution. Our actual voltage, our actual current comes from here. This is our transformer. Takes the main supply and gives us our variable supply. It gives us a supply we want basically. So we can control the supply. This is our clamp meter. This clamp meter can be used to measure the current across this wire. So it uses the magnetic field around the wire to measure the current across it. Similarly, this is our multimeter. We'll be using it to measure the voltage that is being supplied to the wire.
Set up for our experiment. So we are going to start with our main supply and we're going to be supplying the voltage power to this variac right here. What we're going to do right now is we're going to optimize this variac voltage such that it doesn't provide a lot of voltage to the wire so that the material doesn't burn out or anything. Okay? So we're just going to start it for a little while. turn this on, and we're gonna set the variac voltage to about 24 volts. That's almost about it, and we're just gonna turn this off again. Alright, now we're gonna actually start our experiment. So we have set up the variac to 24 volts, so we know that this is gonna be supplying us the 24 volts, and we're gonna be using a stopwatch to calculate the time during which the wire will detach itself. Part of our safety precautions, we are also going to be using this box so that we don't electrocute ourselves. And this process actually happens really fast. The wire heats up really fast, so we'll have to keep a good check on time. And also, in the meanwhile, while we are also noting the time, we also have to check the current on this clamp meter that's being supplied through the wire.
Start our power. We're going to supply the voltage, and as soon as I press this, I'm going to start my stopwatch. So after I've started my stopwatch, I'm going to look at this and see when it detaches. As soon as it detaches, I'm going to stop my stopwatch, because at that time the Curie temperature has been reached. So we're going to start now. So 3, 2, 1. So it took approximately 3.96 seconds for Curie temperature to be reached. We've done this for one time. We repeat this step at the same voltage and same current for different times, like for same voltage, and we note different times to account for human error, and we take the average of that time period. Similarly, then we repeat the experiment for different voltages, and that's how we get our data set. So this is our data set. This is the voltage of the variac. We took different voltages. This is the current we measured from the clamp meter. We did 3 repetitions for the same voltage and same current. And for the first repetition we found this time period, for the second, the third, and then we took their average, these 3. We found the energy using our formula E is equals to VIT, and then we repeated the experiment for different voltages and different currents.
The values of voltages, currents, and time to reach the Curie temperature for different data sets. Now what we're going to do right now is we're going to use one of these values to actually find the Curie temperature. Okay? So what we're using is, the first data that we found was voltage as 24.1 volts, current as 6.7 amps, and time as 12.04 seconds. Now we're going to use these values and put them in our energy balance equation that we figured out before. Putting these back in, we find that 24.1 volts multiplied by 6.7 amps, 12.04 is equal to the mass of the wire that we use, which is 2.35 minus 3 kilogram, and the specific heat capacity of the wire that we use. Alright. And similarly here we took the room temperature to be 27 degrees Celsius. Right. And for this other part of the equation, you're going to go down here, and we found the emissivity to be 0.7, and the Stefan-Boltzmann constant is given as 5.675 exponent minus 3 volts per meter square per degree Kelvin raised to power 4, multiplied by the surface area of the coil that we use. And similarly again here, Tc raised to the power 4 minus room temperature raised to the power 4. But as we can see that this is a very tedious equation to solve manually. So what we are going to do right now is we are going to plug these equations in MATLAB and let it solve for DC automatically. Okay, even though we are going to solve this tedious equation in MATLAB, but at least we should simplify this so that we can have a familiar form of an equation. And so what I did was that I manipulated all of these values to finally get one single equation of polynomial of order 4, which looks like this. So what I'm going to do right now is I'm going to make all of the equations for each of the data sets like these and then solve them on the MATLAB.
This is the TC value for our first data set. This is the TC value for our second data set, third, and fourth. So we plug these, plug similar equations So this was for the first one. So we plugged similar equations into MATLAB and got a value for TC. Now to discount for error, and we took the different values of TC and found an average value. This average value is our value for